In this problem, we have an object. It's moving in a circle. It's bound by a radius of 1.5 meters. And our job is to figure out how fast is it going after a certain amount of time. So it's like there's a rocket on it or something, and there's some thrust, and the thrust is a function of time. But for some reason, the rocket's not appropriately aligned with the motion. Anyway, so you can see that our thrust is actually off at some angle there, just like that. Okay. All right. Well, there are different ways to solve this, and what I want to show you here is how to use angular momentum to solve this. Okay, so remember, I've talked about before, it's good to know different approaches to different problems. Sometimes one way is easier or shorter than another way. Okay, so let's begin by talking just briefly again about angular momentum. And so, whoa, how many times have I done that? Has anybody counted? Let me know if you've counted. All right, so we need a location vector. We're going to cross that with a momentum vector like that. Okay, now, if we just think in terms of magnitude, and we say our motion is limited to a plane, and therefore our angular momentum is going to be perpendicular to that, then what we can do is we can sort of reduce this like this. We can say it's the perpendicular interaction of r and p, which is rp sine theta. Okay. Now, in our particular case, and this is going to happen fairly often, okay, our motion is here. All right, there's our momentum, and so we've got a right angle. And if there's a right angle, that means that term goes to 1. Okay, and so what we're looking at then is just RP, which is to say that H is RMV. That's a P, by the way. Okay, so there's a good relationship to know. All right, again, that only works if you have circular motion. All right, so and r is going to be the radius of curvature for that circular motion. All righty, so our task here is to determine the speed. Okay, so we're actually looking for v. Now, it might look a little bit like we're up a creek. I mean, we know r, we know m, we don't know h. Okay. However, we can find h. We can actually find h really easily. And if we find h, then what we end up getting is this right here. H over r times m. Okay. Very straightforward. So how can we get h out of this thing? Well, that's where our angular momentum, our angular impulse comes into play. So delta h is m dt. Okay. Now we're going to stay, all of our motions are going to be in the xy plane, so everything lines up with k, and so we can just say that this is going to be h final minus h initial, and we're actually starting from rest, which means this term is going to go to 0. Okay. All right, so my integral. Now, what I need is a moment, okay, so which is an r cross an f. And so in this case, we could say it's rf if we adjust for the angle in between the two, all right? So we need the amount of the thrust that is this direction right here. And so that's going to be, it's going to go as 4/5 onto the 10t. Okay, so not quite as much there. Alrighty, so let's put that in there. So we're going to have 4/5 onto 10t dt. Okay, and we got to have a start and a stop, and we're starting at 0, and we're going for 4 seconds, just like that. Okay, so however you want to get that, evaluate that integral is cool. I don't really care, but we're going to get 96. Crazy units again, kilogram meter squared per second, but that is our value for h. Okay, so h is 96. And then all I have to do is plug it in below, and we're good. Okay, 96 kilogram meters per second over a radius of 1.5 meters and a mass of 5 kilograms. Okay, and look at our units. Kilograms cancel 1 meter, and all we're left with then are meters per second. So that's kind of nice. That's what we expect. Work that out, that division, you're going to get 12.8 meters per second. Okay, there we go. Now, like I said, there's other ways to do that. Okay, we could have determined the tangential acceleration. All right, and then from the tangential acceleration, we could have found the speed after 4 seconds. And then using that speed, we could have, well, actually, that would have been all. That's all we would have needed. Okay, but anyway, we would have ended up integrating something anyway. Okay, and I'm not going to take the time to show you algebraically how it's equivalent, but anyway, so this is a kind of a nice little trick, all right, that we can use to do this. Now, notice please that this is F15-22. You have another problem, which I think is F15-21, which is almost identical. The difference is the thrust is not tilted. Okay, the direction of thrust is in line with, or it's tangential to the curve. Okay, so you don't have to worry about the 4/5. Other than that, I think it's basically the same problem. Okay. All righty, so I'm going to do one more of these for you.